Okay. So getting on with optics. On Friday, a week ago, we learned about Snell's Law and refraction. Really important things are where you measure the angle from. So when you measure the angle of incidence, reflection, and refraction, all three of those are measured from the same reference, that reference being the normal to the surface. So whenever you're doing one of these problems with geometric optics, the first thing to do is to draw that normal so you can identify the angles. And so you're going through the homework problems that are due tonight, if you have not done them already, identifying which the angles are that we're relating with Snell's law or with our law of reflections is super important, which is why I think we had it on clicker questions twice, because it's really vital. And so, you have, for instance, a question that has psi marked as this angle and says, what's psi? Well, you have to use the definition of angle of incidence and angle of reflection and the law of reflections. What is the law of reflections? That's Snell's law. That is a law, but it's Snell's law. That's for refraction, for reflection. It's the very simple one for reflection. It's the same. Theta incident is equal theta reflected. Well, this psi is neither the incident nor the reflected angle. It's the complement of the reflected angle. So complement means the two angles add up to 90. So you just use a two-step. One is the law of reflections, and one is that psi is the complement of the theta reflected to find what psi is with regard to the incident angle. And then if you're using Snell's law, which is the one that, was it you? Yeah, the one that Gila was quoting for us. Snell's law is is the equation that governs what happens when light goes from one material to another material with a different speed. And on Friday, we had all the demonstrations where we saw that the light changes direction. It bends toward the normal, that is, it deviated in this direction if you go into something slower. It bends away from the normal if you go into something with a higher speed. And then you use Snell's law to relate the indices of refraction, which relate to the speed. Remember, index refraction is the C over V. What does C stand for? It's not just speed of light. Those are the first three words. In vacuum. It's very important that you have in vacuum. Otherwise, you end up with things that are like, the speed of light is 1/2 the speed of light. And you're like, wait a minute. That doesn't work out. The speed of light can be 1/2 the speed of light in vacuum. Sure, no problem. So V here was the speed of light. And I'm going to add 3 more words again. Or 2 more words. In medium. The medium is whatever the light's traveling through. The speed of light is slower in any medium that's not vacuum. So vacuum is always the fastest possible speed for the speed of light. So that's the index of refraction. So if the index of refraction is bigger than 1, then it's going slower than the speed of light in vacuum. If the index of refraction is smaller than 1, you've just broken the laws of physics, because nothing can go faster than light in vacuum. All right, let's do a problem and then go on to new material. A beam of light strikes one face of a window pane with an angle of incidence of 30 degrees. The index of refraction of glass is 1.52 degrees. The beam travels through the glass and emerges from a parallel face to the opposite side. Ignore reflections. Find the angle of refraction for the ray inside the glass. So I am failing miserably. I put a ruler on here and it's not working. Well, forget the ruler. If it's not going to work, we won't do it. Erica, be my reference that the ruler has been working in the past. So here's my pane of glass, drawn without aid of the ruler. I'm going to have my incident light comes in like this. Whoops. Yeah, this totally isn't working. Somehow, I got part of a line drawn let's just say that Microsoft doesn't have everything fixed yet. If it goes from air, which has an index refraction of 1. Now I said 1. Nothing can have an index refraction of 1 except vacuum. Everything else has to be bigger than 1. But air is only slightly bigger, like 1.00, I think it's 0.1 or something like that. We'll see in a couple slides. So it goes into the glass. What direction is that light going to deviate? Is it going to go more vertical or more horizontal when it goes into the glass? Good, Alex. Okay, more vertical, Alex says. More toward the normal. Why more toward the normal? Because it's going slower in the glass. If you go into a medium where it's going slower, as indicated by a higher index refraction, then it bends toward the normal. And since the normal is vertical here, it's going to bend toward the normal. So I said one of the first things to do is always identify the normal, and then I can say, aha, it's going to bend toward the normal. So instead of going straight, it's going to bend more like that. Gets to the second surface. Now it's going to go back into air again. So what direction is it going to deviate when it goes into air? Away from the normal, because now it's going from a slower speed to a faster speed. And so now it's going to deviate to something like, well, something like that. So I have a path, a proposed path that my light's going to take. Now keep in mind, those should all be straight lines, and they would have been if the ruler tool would have worked. Now the next thing I need to do is to say, okay, I'm going to use, because I have refraction, I'm going to use a certain law. What's the name of that law? You could call it the law of refractions, but that's not the technical name. It's named after a dude. Snell's Law. We're going to use Snell's Law, which says N1 sine theta 1 equals N2 sine theta 2. So I need to look at this and say, okay, where's theta 1? Where's theta 2? Where's theta 1? The angle of incidence at the first surface. Okay, now, just going by the words you said, which I don't think is what you meant, the angle between horizontal and vertical is 90 degrees every time.
Your incline.
Okay, that between my incline and which one? And the normal. There's my angle 1, the angle between the normal and the incident ray. Not between the surface and the incident ray, but between the normal and the incident ray. Okay, what about theta 2? Theta 2 is the angle of refraction. What's that going to be between? It's never the surface. It's always the angle between the normal to the surface and the light ray. So theta 2 is this angle here. And then we have another set, so I'm just going to go to theta 3. Theta 3 is going to be the angle between the normal to the next surface and my ray. And finally, there's theta 4, between the normal to the last surface and the exit ray. So I've identified all of my angles. I haven't even looked at the problem, okay? That's always a danger. You should read the whole problem before you get started, but I'm sure I'm going to need this. Question, Gila.
Can we assume that the normals are parallel?
The normals, because it says that we have a plane of glass, the plane of glass should have the sides normal, which means that the normals are also normal. Yes, it says here parallel face on the opposite side. So it tells us that. So that means that these normals are parallel to each other. Now, Gila was thinking about something here. If these normals are parallel to each other, what does that tell you that's important? Theta 2 is equal to theta 3 is a straight geometry that Gila deduced because the two normals are parallel, and theta 2 is the angle between the refracted ray and one normal. Theta 3 was the same refracted ray and the other normal. If the two normals are parallel, then one of our fundamental rules in geometry is that when a line crosses two parallel lines, the angle between the lines is the same. So this was a geometry deduction that Gila came up with. And it's an important one. Now let's read the question. Find the angle of refraction for the ray inside the glass. So that is find theta 2. What do we know? We're given the angle of incidence 30 degrees. What is that angle of incidence in our labels here? Theta 1, 2, 3, or 4? Theta 1. So we were given that theta 1 is equal to 30.0 degrees. And then we want to find theta 2. How do I relate theta 1 to theta 2? I just apply Snell's Law. So I'm going to have n1 sine theta 1 equals n2 sine of theta 2. I want to solve for theta 2, so the first thing I do is I get my trig function alone. So that gives me sine of theta 2 is equal to n1 over n2 sine of theta 1. How do I find theta 2 if I have sine of theta 2? I just need to use the inverse sine. So but of course, inverse sine of sine, by definition of the inverse function, is theta 2. I'll put in my numbers now. Sine of 30 degrees is one that hopefully everybody memorized when they were in high school. It's 1/2. So this is equal to inverse sine of 1 over 3.06. 3.06. It turns out that 2 times 2 is 4. Be good math. So what do we get for that angle? Okay, 19.2 degrees. So we have theta 2 is 19.2, which means theta 3 is 19.2. Now we can check what Alex said at the beginning. Did it actually bend toward the normal? Yes or no? Yes, it did, because it has a smaller angle of refraction than its angle of incidence. Now, show that the rays in air on either side of the glass, the incident and the emerging ray, are parallel to each other. There's a couple ways of doing this. One is a brute force method. One is a little more elaborate, pretty method. How would you do it, Brandon? The first one, the more brute force method was the first one. So the more brute force method would be simply let's calculate what theta 4 is. So if I want to calculate theta 4, I'm going to have on the second surface, I'm relating theta 3 and theta 4. So I would have n3 sine of theta 3 equals n4 sine of theta 4. Solving that for theta 4, I divide both sides by n3 or n4. And I'd have now I don't want to do it the brute force method. I want to do it the prettier way. So I'm not going to continue it by putting in numbers. Instead, I'm going to do substitutions. We have N3 equals N2 because both are glass, and N1 equals N4 because both are air, and theta 2 equals theta 3 because Gila said so. Okay, because we had parallel surfaces. I mean, Gila did say so, but that's our geometry reason. So I'm just going to make those substitutions. So I'm going to have sine of theta 4 is equal to, instead of N3, I'm putting N2. Instead of N1 or 4, I'm putting N1. And instead of theta 3, I'm putting theta 2. But then if we look up to what we've already done, that, oops, wrong one. Well, I solved it the wrong way. Solve it the other way. That, and taking my initial equation here, and if I divided both sides by N1, I would have had sine theta 1 is equal to N2 over N1 sine of theta 2. Close. There we go. So those two equations in the box are identical, except for one says sine theta 1 and one says sine of theta 4. Since they're identical except for theta 1 versus theta 4, that means theta 1 must equal theta 4. And I didn't have to do any of the intermediate calculations because it came out no matter what. If I have parallel faces and it's the same material on both sides, they're going to be parallel. Question, Lauren?
What would happen if you don't have parallel sides, like with stained glass?
If you don't have parallel sides, then you're going to have to go ahead and do the work. Yeah. You'd have to do the brute force then. So that is, I mean, that's how we use Snell's Law. You know, you have your homework doing Snell's Law 5 different ways because we need practice with it to actually understand, yes, bends toward normal if you're going to slower, bends away from normal if you're going to faster, and so on. Now, 2 fun things. The Mirage, as Bugs Bunny would call it. We've all seen Mirages, although we may not recognize them from time to time. From my own experience, when I was a little kid, we took great summer vacations where we had the travel trailer and we get in the car and we go driving across the Mojave Desert or whatever. And I remember as a young sprout, like 6 or 7, we're driving across the Mojave and it's hot as blazes. And I look up ahead and I see water on the road. And I'm like, sweet, we're gonna have a little cooler in here. And we drive on, and we don't get to it. It drives me crazy because I want to get to that water, and we never got to it. What was I seeing? Okay, the word is mirage. Don't say mirage. What was I seeing when I thought I saw water on the road ahead of me? Because it clearly wasn't water on the road ahead of me. It was what? An illusion. An illusion. Okay, it is. We can call it an illusion. I'm happy with that. But what was I seeing? I was seeing something physical. What was I actually seeing? It's an illusion because it wasn't where I thought it was. But I was actually seeing something. Now, before I answer, let's go with the illusion. let's say I'm an illusionist and I have a cool trick. Oftentimes that cool trick is as simple as a mirror. You set up a mirror like at a 45-degree angle and you have so the wall over there looks like the wall over there. And people look in that mirror and they just think they're looking through because they don't realize they're seeing that wall over there instead of that wall over there. And so, physics demonstration that you can do is like have a mirror that you straddle and go like this, and it looks like you're flying because you have this foot's off the ground clearly, and then they see the reflection of that. They just think it's the other one, and it looks like you got both legs off, you're Harry Potter or whatever. So it is an illusion, but what you're seeing is illustrating this picture. You have light, and what I was seeing was, of course, there was a sky up here. That's not the color of the sky. There's a sky up here, and light from the sky, of course, is going in all directions. And so sitting there in the car, I'm looking forward, and that light from the sky comes down to the road. But as you get to the road, the air gets hotter. Right? I said I was in the Mojave Desert. It was hot. And you have a black road. That black road is going to absorb solar radiation pretty effectively. And so it's going to be hotter than other surfaces around. So the air just above the road is going to be heated by the road, and it's going to be ultra hot. Well, if the air is hotter, light goes faster through it. And if light goes faster through it, if I have a layer here with a slower speed on top and a higher speed on bottom, and the light comes in like this, it's going to bend toward or away from the normal if I'm going into a faster medium. It's going to bend away from normal. So instead of going straight through, it's bending, so it's coming more like this. So the light comes down, and when it hits that, it starts curving like this, and goes all the way around and comes back up. And so I'm looking down at the road, but what I'm seeing is sunlight, skylight, that came down and was bent back up into my eye. That's what's going on with the mirage. It's not like you're seeing something that doesn't exist. You're seeing something in the wrong location. So an illusion is a good term for it. In the Bugs Bunny movies or videos, he sees trees and a nice pool. I didn't see trees there. Why? Because I was looking at the sky. There's no trees in the sky. Bugs, that's cartoon. So it looked like water. It shimmered. Why did it shimmer? Because the hot air is rising and moving around, and as it moves around, the refraction is going to be changing directions. So that's what causes the shimmer. We have exactly the same thing when you look at stars in the sky and they twinkle. The twinkling of the stars is because you have air currents that are different temperatures, hence different speeds of light. And that causes the light to bend in different directions as it goes through the different air currents, making it so we don't see a single path, but we see alternating paths. And it looks like it's twinkling or moving around. Now that's the common mirage. So this here is a photograph in black and white, as lovely as that can be, that's supposed to illustrate a mirage. I think you're supposed to be seeing the mirage like here, but you're clearly seeing the trees reflected off the ground, or not reflected in this case, but refracted. So that's what a mirage is. That's the kind of mirage you see when you're driving. And if you've never seen a mirage before, simply drive from here to California. Just get on Highway 80 in Lincoln and drive until you're in Lincoln, California. You will see a mirage. Because when you go through Utah, you're driving through these salt flats. And if you look down the salt flats, you will see mountain in the background. Looks like it's reflected off the salt flats. It's not reflected, it's being refracted. The light's being bent up. And so you see, like this picture with the trees, the mountains down here. It's very cool. And it's very boring on that drive, so you got to have something to keep you occupied. Here's another kind of mirage. If you are over a body of water, you can have an inverted thermal layer. The water is going to keep a cooler temperature than the air on a hot day. And so you're going to have cooler temperatures with the air temperature going higher as you go up. In that case, you're going to have refraction, light coming up from the water is going to be refracted by that inverted thermal layer and come back down to you. So in that case, you look up in the sky and you see ships sailing in the sky. Of course, those ships are going to be upside down sailing in the sky, so it adds to the confusion of the effect. But that's another type of mirage. That's a mirage where you have warmer air above the cooler air. The mirage, when I look at the road, is cooler air above the warmer air. So now, hopefully you understand what a mirage is. And of course, you know the Bugs Bunny isn't right in saying mirage, just like Eddie Murphy's not right in saying battery. Prisms. We're going through a couple interesting topics here. A prism. What do you use a prism for? For what? To look pretty. That's what we use prisms for all the time these days. If you were a physicist 100 years ago, you'd be using prisms for all kinds of optical duties. These days, we don't use them nearly as much. The prisms for beauty is what I want to focus on right now. What makes the prism pretty, Ela? The colors, the pretty colors. Back when I was in grade school, good old Miss Burchell had this prism. And if we finished our schoolwork early, okay, everybody has to add these 10, 100, million, addition problems. When you're done, if you're done early, you can come and you can borrow the prism off my desk. And of course, me being the nerd, when I was done, I'd come and I'd get that prism and I'd hold it up to my eyes and I'd walk around, because everything looks different. And I thought that was cool. My other classmates, being a little more artistic, would take it up to the window and look at all the pretty colors coming through, which is what Gila's referring to. There's nothing wrong with either one of these, mind you. Doesn't matter if you're artistic or a nerd. What's going on is a simple thing we call dispersion that makes the colors. What is dispersion? The speed of light in a medium varies by color. That means red light has a different speed of light than blue light if you're in something other than vacuum. In a vacuum, everything has the same speed. But if you're in glass, the speeds will be different. But if the speeds are different, how does that affect the path the light takes? Okay, if the light is slower, what happens? It's actually more refracted. The bigger the change in speed, the bigger the refraction. And so if we look at the light going through here, we see that white light actually contains all of the colors of the rainbow. So that's all of the colors mixed together in roughly equal proportions. When you put it into the prism, we have the red light bends the least. So that means the red light bends the least, therefore is the fastest, because it's the smallest difference from the speed of light in vacuum. The magenta light bends the most. I said magenta. That's absolutely the wrong term. Violet is what I meant to say. So it's the slowest. So we have the light separates because we have different speeds of light for the different colors. And that relationship is called dispersive relationship, the dispersion of light, spreading it out by colors. So that's That's why we see this in prisms, and we will talk more about it in just a moment when I get to talking about rainbows. But first I have to talk about total internal reflection. We had a rule that said if you go into a slower medium, the light refracts toward the normal. If you go into a faster medium, the light refracts away from the normal. And that was governed by Snell's Law. But Snell's Law says n1 sine theta 1 equals n2 sine theta 2. But there's a limit. The biggest angle you can have for refraction is 90 degrees. What is the sine of 90 degrees? 1. If you had a bigger angle than 90 degrees, what happens to the sine of that angle? Well, it goes smaller again. It can't get to negative, but it goes smaller again. So you can't have any answer that would say that sine of theta 2 is bigger than 1, or that the angle is bigger than 90 degrees, which makes perfect sense because if it refracts by more than 90 degrees, here's my surface, it comes out and bends more than 90 degrees from the normal. That means it stayed in the material. It didn't go through. It did not refract. So anything that would have an angle of refraction bigger than 90 degrees would not be refraction at all. It would be reflection. But if it reflects, we have a different law, the law of reflections. And so we have a critical angle, the angle of incidence, where the refracted angle is 90 degrees. So the critical angle is the angle of incidence where the refracted angle is 90 degrees. So here's Snell's law. Angle of index refraction of the incident material times sine of the critical angle is equal to the index refraction in the second medium times sine of 90 degrees. So you solve right away and you get theta critical is equal to inverse sine but what did we say sine of 90 degrees was? 1. So nobody, oops, that's a 0. Nobody ever writes sine of 90 degrees. They just say that's a 1. And so theta critical is just the inverse sine of the index of refraction material 2 divided by index of refraction material 1. If your angle of incidence is less than theta critical, that is if you're closer to the normal, then the light's going to be refracted through. If your angle of incidence is bigger than theta critical, you don't have a refracted ray anymore. You only have an internal reflected. And once again, last Friday, a week ago Friday, we saw that demonstrated with the prisms. Now we have some math to back up why that should happen. So the critical angle is a simple calculation. It's the calculation of what angle of incidence will have angle refraction that's 90 degrees. If your angle of incidence is bigger, totally reflected. If the angle is smaller, you're going to have some refraction, some reflection. Now a question that you have no background in. I didn't hit start. And it's not working. Give me a second. We'll try this again. Reset the session. Set that one. During polling, I'm not, nope. Okay, that should all be right. Please work. Okay, it's working now. Lauren is the first one in. No one else has answered, just so you know. Why is the sky blue? Unless people are worried about being called out on this one, I'm not going to call on somebody to answer because I haven't lectured over it yet. When we get it the second time, I'll call on somebody to answer it. Okay, waiting on James, Jeffrey, Angelina, and Corso. Well, Corso's not here. James, Jeffrey, Angelina. Jeffrey, Angela. Okay. And get in there, Angela. Okay. So we have 32013. Hey, it stayed. There's our answers. Pretty astonishing that 13 are correct. We haven't talked about Rayleigh scattering at all. A lot of people think that it's one of the first two. You guys did. I'm guessing that must have come from the reading quizzes. The sky is blue because of Rayleigh scattering, which is you have light scattering off of little scattering centers, molecules of oxygen, nitrogen in the air, that are smaller than the wavelength of light. Rayleigh scattering is the scattering off of those. And Rayleigh scattering is the strength of the scattering, that is the percentage of light that's scattered, is proportional to the wavelength, well, 1 over the wavelength raised to the 4th power, which means that short wavelengths, blue is our shortest visible wavelength, well, violet, blue, with a wavelength of about 400 nanometers. Red is our longest visible wavelength with a wavelength of about 750 nanometers. And if you take that 400 to 750, that's almost a ratio of 2. 2 raised to the 4th power is 16. So blue light is scattered about 16 times stronger than red light. So the light from the sun, what color is the light from the sun? White. Oftentimes we think it's blue or yellow, but that's not right. It's white. So we have white light from the sun coming down, and then the blue light is being scattered away in different directions 16 times stronger than the red light. So if you look at the sun, it has 16 times more blue light that it lost compared to the red. So it's white minus the blue, effectively. But if you take away blue from white light, you end up with yellow, making the sun look yellower than it really is. And if you look anywhere else in the sky, you're seeing light from the sun that went over here and then was scattered at a random angle. And so you're seeing light that's primarily blue because the blue is scattered by far the most. So anywhere you look in the sky, you're seeing sunlight that was scattered off of the atmosphere with blue light scattered the most. Alex? Yes, violet. I use blue as the term for that end of the spectrum. Our visual acuity drops off considerably as you go from blue into violet. And so I think most of us see the sky as blue, not as violet, because of our visual acuity being what it is. Also, the sunlight itself drops off quite a bit when you get to the violet. So it's the Rayleigh scattering that's causing the sky to be blue. Now, I had another answer here that's another one you should know nothing about unless you've read up. And that's me scattering. It's a Chinese dude. Me scattering is the scattering of light off of things that are larger than the wavelength of light. So once again, what's the wavelength of light? For visible light, that's 400 nanometers, 400 billionths of a meter, to 750 nanometers. So if you have some particulate that's bigger than that, i.e. water droplets, then you're going to have me scattering. And me scattering is the same strength for all different colors. So if you have white light from the sun that comes and hits water droplets, you're going to have all of the colors scattered equally, and you're going to see white. So clouds look white because of me scattering. The sky looks blue because of Rayleigh scattering. Make sense? Are we going to do any calculations with those? Nope. Just things that we need to understand. Hey, it's this interesting scattering of light from different size objects that makes the difference in the color. Now, I said clouds are white. If you have a thunderhead, you'll get dark clouds. Why are they dark? Okay, because they're absorbing some light. They're so thick that light is being absorbed or being scattered completely away, not getting through. Now, the answers that people usually give talk about water. So here's some properties of water. Water has an absorption spectrum shown there with the blue line. And you see that we have wavelength on the bottom. 100 nanometers is on the left side. That's very short wavelengths. That's ultraviolet. Going to the right, you can see where the visible spectrum is, and you see that water does absorb more red than it does blue, which is why water does tend to give you a blue color, because it is absorbing more red than it does blue. But that's not why the sky is blue. That's part of the reason that water looks blue. Now to rainbows. We get all the fun stuff today. Rainbows. My first or second year teaching physics, I only talked about the first order rainbow, and then on the MCAT there was the second order rainbow. I was so embarrassed that I hadn't covered the second order rainbow. So I want to make sure I cover both. Rainbows. I imagine we have all studied Genesis, where it says, I do put my bow in the cloud, that it will be a sign between me and thee, that I'll never again destroy the earth, or something to that effect. And so there are some people who take that to say, no, this physics stuff can't be it. It's just a thing, a miracle God does every time you see a rainbow. And so I want to make sure I at least talk about this just a bit. As a scientist, I believe that God set the laws of physics up. And so he made it so rainbows will appear. And, when he told Noah, I should shift up a little bit and say, when he told Abraham, when he told Noah, he put his bow in the sky, what was he doing? Well, I think that there was a physical change in the Earth's atmosphere. Before the flood, you had one atmosphere. Afterward, you had a significantly different atmosphere. A traditional belief is that before the flood, there was a layer of water somehow in the atmosphere that collapsed and is no longer there. And we know that the Bible says that evening and morning dew watered the Garden of Eden. And so I tend to think that, there's a somewhat consistent story in the Bible that's a little hard to explain scientifically, that prior to the flood, there wasn't rain. You didn't have the water droplets in the air sufficient to form a rainbow, hence you didn't have rainbows before the flood. But after the flood, we do have the water droplets in the air. We do get the rainbows. Rainbows are a result of light refracting into a water droplet, having internal reflection on the water droplet, and then refracting out. So it's a rather complicated process. So here I have a picture of the first order rainbow. By the way, this picture here, that's showing the index of refraction of light in water. And so you can see this is red light has the index of refraction that's about, this is actual measurements here, about 1.33, just a little bit bigger. And blue light, or violet, as Alex pointed out, has a measurement of more like 1.345 for the index of refraction. It's not a big difference in the index of refraction, but it exists. And because you have a difference in the index of refraction, you're going to have a dispersion, a spreading of the colors when it refracts. So if we look at the water droplet, we have light from the sun that comes into the water droplet. And at the first surface it refracts, which one is going to be bent more? That is, deviate more from a straight path. The faster speed or the slower speed? The slower. Because the light is fastest in vacuum, the one with the biggest shifts, which means the slowest one, is the one that's going to have the biggest bending. So the blue light, the slowest one, has the biggest bending. The red light has less. So we have the colors separated. You get to the back of the droplet, and you have reflection here. And because of that reflection, you have the two beams cross over each other. So the violet goes like that, and the red goes like that. My lines are exaggerating, so we just see that they cross. And then they come out, refract again, and they're now different angles. And so when I look in the sky, if I look at the right angle, I'll see red, and a different angle, I'll see violet. And in between, I'll see the colors in between. So the rainbow is based on the angle between the incoming sunlight, the water droplet, and me viewing it. And we can use our physics calculations with those indices of refraction to get the actual angles. So here's what you see when you look at a rainbow. When you look up higher, that's a bigger angle. You see the red light because the red light was deviated the smallest amount. You look at lower water droplets and you see the blue light, or violet as it shows here. So you see violet at the lower angles, red at the higher angles. And what are those angles? They're between 40 and 42 degrees roughly. I thought I had that on this slide. Maybe it's on the next one here. Yeah. Between 40 and 42 degrees are the angles for seeing the colors of the first order rainbow. Now, what is that angle between? That's between the incident sunlight and the exit light from the water droplets. So you have a whole bank of water droplets. If you look at the lower ones, you're going to be seeing the blue. You look at the higher ones, you're going to be seeing the red. Why does it form a circle? Right? Rainbows are arcs. Why are they arcs? If you take a compass and you draw 40 degrees, that's going to make a circle if you go around. Right? So you're going to have the inside is 40 degrees, the outside is 42 degrees for a rainbow. And if you took the center of the circle you make from that arc, go through your eye, keep going back, that's where the sun is. Because you're seeing the rainbow at an angle of between 40 and 42 degrees from the direction the sunlight was coming in, so going from the sun through your eye to the center, and the angle you're viewing. So that's the first order rainbow. Here's a picture for the second order rainbow. What's different about the second order? It has two reflections instead of one. And because it has two reflections, it has the light crossing over twice. With the light crossing over twice, you reverse the directions. Each time the light crosses over, that is the red crosses the blue, you reverse which color's on the center. And so since it reflects twice, it crosses over twice, and it inverts the order of the colors. So the first order rainbow has blue in the center and red in the outside. The second order rainbow has just the opposite. So, oh, come on, where's my pictures? Here's a picture showing the first and second order rainbow. So this is the first order. Here's the second order. Notice what you see when you look at the sky. Underneath the first order, bright sky, right? Between the first and second order, dark sky. This is actually called Alexander's dark band, the region between. The reason is, in Alexander's dark band, you have scattering of light, but it's all being scattered away from you. And so you're not seeing any scattering back from the water droplets in the sky. On the inside, you are seeing some scattering back, and that's why it's brighter.